But one of them, actually, one of them is arguable. There you go.
Well, wait. Why don't you wait till after class?
The answer sheet right here. Really quick.
Because the thing is, the mistake that I did, that he did actually, is because helium is monatomic, that's why I used the 3/2 there.
Yeah.
For that.
That's not the only mistake you made.
Yeah, well, I don't understand what was wrong there, though.
Wait. Say that again?
I don't understand what was wrong here.
And so you lost points.
Yeah, I know. Well, apparently I need to find out why I did wrong.
Right.
You win this time.
Was that the word?
I forgot to fill up my black pen.
How often do they die?
Too often. Yeah, like twice a week. Yeah. Well, the black one, because that's. I'll just steal a new one. I won't even bother to refill it.
Yeah. I mean, he has like 6 boxes of those.
All right. Hey, let's go ahead and get started because it is a few minutes past time and we are a little behind the syllabus and we've got a lot to do and I want to do as much as we possibly can before the semester is over. This Physics 123 class I think is a great class because we go from so many topics from back and forth, but there just never is enough time to do complete justice on any one topic. And again, I got to keep telling myself it's not designed that way. It's designed to get a good first step and then that's it. And so we had to stop short a little bit in the thermodynamics, and likewise we're going to see the same thing in the optics. But I do want to make sure I can show you as much as I possibly can. And so with that said, for today I did something a little bit different, and that was the following. I went ahead and placed the tests out here. I trust that you guys have picked them up, and I'm going to pass this out. It looks like some of you got it. What this is this is the solutions to the test. Step 1, step 2, and all the way through. They're kind of condensed so I can fit them on one page, but the answers to all 5 of them are on that one page. And so I thought a good place to get started would be to have you take one, and then after class or in lab, you still will probably have questions on how you do things, particularly the entropy one, which seemed to, and rightfully so, since it was the last thing and the hardest thing that we did, give students a little bit of troubles, but it is involved in an integral. So I would encourage you to look at there, and you'll see that you just did a division, not an integral, and in calculating the entropy here. And so entropy, like heat and like work, depend what path you're doing. They are path dependent. You have to go back and do the integral. And so with all that said, I'm going to do something that is a little different than normal. I'm not going to run through the first 45 minutes and go over the test. I'm going to say, all right, you probably have some questions. Hopefully this solutions will work them out. And if not, come talk to me during lab or Dawn during the MC or Dawn just anytime. Yeah.
Can you just put the grading scale?
Point-wise? Yeah, there was actually, I hope you thought it was straightforward. I tried to make it straightforward. There wasn't as much as, like on the first test where part C, some original thought, something you hadn't seen before. Everything that on there you had seen before. And so the grading scale, let's see, I think the range, if I remember, I want to say 39 to 100. Average. This class average was 83.9, and the next section was 84.1. So I was glad to see that they came out to be the same. Point-wise, in terms of grades, was that what you were asking? Keep this in mind that an A grade is between 100 and 90% and 100 overall. So that means if your test is greater than 86% and you do all the homeworks and labs, you will get greater than 90% overall and you will get an A. A B is in this range of 80 to 90%. So that means if your tests are greater than 73% and you do all the homeworks and all the labs, then your overall average will get above 80%. C. C is a bigger range. And I can't remember off the top of my head now what that number is. But it doesn't sound like you were interested in that one. You were in these right here. So, okay. So then I'll go through and somewhere in there. Okay. All right. Well, like I said, if that helps, in terms of doing the pass back of the test, I think so. And again, since most of you did very well on the test and it was straightforward, I thought the solutions, if you just saw it in front of you, most of you would see right away, like, oh, I missed that, or maybe I didn't realize it was monoatomic, or maybe diatomic, or maybe I didn't realize it was constant volume, or whatever the case may be. And so let me use this then as an opportunity then to say, all right, let's jump into our optics, because the optics chapters have some, not only some real neat stuff, but actually some pretty long involved derivations that are worked out. And maybe part of me will skip the derivations. The other part of me realizes that you got to see these derivations before you can really apply that, so you know where this stuff came from. And so that starts with our lenses. And so if you guys remember back on, when did we, I guess it was just Thursday. So we took the test on Tuesday, but then we did our optics calculations. We saw this. And so let me turn the laser beam on again and say, all right, what happens if, oh, and I wanted to grab these lights, although maybe not today. We won't do nearly as much lights out on the blackboard as last time. But to get us started, I do want to remind you that here is the goal of this chapter. This chapter is to say, let's form images. Let's take the law of reflection together with the law of refraction and see if we can redirect the light, or what you might call control the light, to make images. And so our first step here is to look at mirrors. And so mirrors would follow the law of reflection. And so when we left on Thursday, we got started with our mirrors. We took a flat mirror. We started off, whoops, I grabbed the wrong one there. We started off with a flat mirror and something like this. I'll turn down the lights a little, whoa, way too much. See if I can find the lights again. Can't even turn them on. I can't find them. There we go. Let me do the incandescent here a little bit. All right. And so if I put a flat mirror on here, what will happen is the light will come in and the angle of incidence will equal the angle of reflection. If you recall then, we got started with a little bit of geometry, and I say a little bit because today I want to do a lot of geometry and trigonometry and look at more complicated mirrors than just the flat mirror. But the flat mirror, we did something like this. We said if you had an arrowhead that had a height h and was a distance p away from the mirror, what would happen is if you drew two beams of light, and let me do blue for my beam of light, the first one hitting the mirror and going straight back, The second one hitting somewhere on the mirror. It doesn't matter where, but I'll go ahead and pick the perpendicular distance from the bottom of the object. If you trace these back and this back, it will give you the impression that the light is coming from back inside of the mirror, and we called that a distance Q. And we went through some geometry to show then that this triangle out here in green and this triangle here in orange were congruent, right? And when they're congruent, we can then say P equals to Q. We could also say if the height of the image is H prime, then the height of the object is H. And so we left off with this first mirror, which I hate to use the word boring mirror, but that is the idea. This is a boring mirror. Useful? Yes, but boring. All it ever does is give us an image that is exactly the same size and just as far in the mirror as in front of the mirror. It gets more interesting now when we curve them and which direction we curve them and where the image is located.
Why did you choose those lights? Why not other light?
Doesn't matter which ones I pick. Give me any two and I'll come up with the same thing.
Slightly higher above?
Instead of this one? Or are you talking about this one or this one? So maybe in orange I'll draw another set. Okay, so you want me to draw it from here to? Right here? Okay, so if I did this, it would bounce off and do that one. Do you want me to do a second one with this one, or just go ahead and do that one and that one?
Yeah, so what makes you choose which light to do?
And my point is it doesn't matter which one I do.
Okay, so
If I were to say that angle equals that angle from the law of reflection, and then draw this ray back to somewhere, and then do my geometry, that angle equals that angle, which these are right angles, so all the angles are equal, they share that side, they're congruent, and then P equals Q. I know that was kind of fast, but that's exactly what we did last time. So, no, there's nothing magical about this ray. I drew it so it hits here. But if I would have drawn it to hit anywhere on here, I would go through the same geometry and it would come from here. Which, by the way, keep that in mind, because of that, what that means is I only need to draw two rays to figure out where the image is. But what that tells me is all the rays come from there. So a ray that would be doing this would have the appearance of coming from here. A ray that does this would have the appearance of coming from there. A ray that does this would have the appearance of coming from here. And so, again, I only need two to kind of go through the geometry. But as you pointed out, why does it have to be those two? It doesn't. It would be all of them. And so we'll take advantage of that. So where we left off, I'll turn on the room lights here, was a little more interesting. Oh, actually maybe I should have left the lights off there. I'll even do those. Is what if the mirror was curved? And if the mirror was curved, we pointed out that the light would hit at some point which we are going to refer to as its focal point. And so if I come over here and draw a curved mirror and label this as point F, what I mean by point F is the place where the light, if coming in straight or parallel as we'll call it, parallel being parallel to this dotted line, which is really what we'll call the optical axis of it. But we learned, and this is where we left on Thursday, that there is a mathematical relationship between this focal point and the radius. I'll call this point C for the center, meaning that this little piece of mirror is part of a giant sphere. It might be kind of hard to see since it just has a little indentation, but follow that circle around, and this is a small piece of a big circle, and so it has some radius of curvature. Of course, this model, you can see a lot more of the curvature, and you would see it definitely has a radius of curvature. This one's also pretty big that I think you can see it's got a radius of curvature to it. Okay, well, I'll start there and then continue on. But the last thing we did on Thursday was, what's the mathematical relationship between this magical focal point and the radius? Yeah, and so the radius of curvature is cut in half, will give you the focal point. And so we went through a little geometry. And remember, we made a little approximation in there. And so we're going to continue with that approximation as we continue on here. And so all of our optics are really more approximately true than they are exactly true. To be more exactly true, we would have to do some harder mathematics, some harder geometry, some harder trigonometry. And for some of you, that day will come. It will be in your next optics class, and so this is, part of your beginning education, your what we would call an introduction to optics. So we make some approximations, and then the reality is, if we wanted things more accurate, we would have to take that next step. But here's what I want to do. I want to work with this curved mirror in the same way we did the flat mirror back on Thursday. All right, let's give it a try here. Let's take an object. So here's my arrowhead. And so just like on last Thursday, we took an object, we placed it in front of the mirror. Let me do that for this curved mirror. Now notice where I placed it. I deliberately placed it kind of far out there. And so notice that I have placed an object, and what's going to be important is that it's further than the radius of curvature. And so if I were to take this mirror and ask you to look at something that's kind of far away, like yourself, do you see your image in here? Do you notice anything about it? Can't see it?
No, just the light.
Yeah, and hopefully you will see that the image of things that are far away are upside down and smaller. But they can also do other things too. And that's why this is not a boring mirror. It can do many things. But let's talk about this first case here. So let's draw some rays here. So I'm going to take this ray that goes parallel. And let's draw, yeah, I could draw any ray. But this one I know something about. What do I know about this ray? Yeah, and that's why we spent time looking at this, is because I know it will go to the focal point. So this ray will hit the mirror, bounce off, and go through the focal point. Is there a second ray I know anything about? Good, exactly the reverse of this. So remember, the law of reflection is what's going to determine the behavior of our mirrors. And so if we do what I would call the reverse process, that is, what would happen to a ray that would be coming from the top and go right through the focal point and hit the mirror? What would happen to that one? Yeah, that one would bounce off and go what I'll call parallel to the optical axis, right? And so this point right there is where somebody standing over here would see, right? They would look in here and say, this ray going to my left eye, this ray going to my right eye. Trace it back. Where does your brain calculate where the light is coming from? And in this case, it is coming from right here. Notice, in front of the mirror. This is why I showed you this one, and for other reasons, last time, is because most of you, I think, are familiar with flat mirrors. And you're familiar with images that are formed behind the mirror. But when the image is formed in front of the mirror, it does have a different look to it, if you will. It's as if the image is real, ghostly even, right? And of course, the people who do this the best is the Haunted Mansion at Disneyland, and I'm sure you've been there. They love to make images, and real images, because it does have a haunting effect, if you will, of, hey, the light is not coming from back there somewhere, behind the mirror. It's right in front of me. And so the light has been redirected to say, come together here, and then come out from that point. And so there is the image. In a minute, I'll pass one around where this image is actually formed right here. And you're going to want to reach out and grab it and touch it. But there's some other things I want to show you first before I get that one. But I think that's why this one is kind of neat to see. Also, what does it say? It is upside down. Now, I guess I really haven't proved it was upside down as much as I've drawn the light from the arrowhead, so this is the arrowhead. But if I did the same logic from the bottom of it, I would get the light right here at the bottom of it. And so this image is not only in front of the mirror, but it is also inverted. It is also smaller. And so, again, I think you see the smaller in here. I think you also see the upside down. Now, the fact that it's in front of the mirror may not be so obvious on this one, because you're so far away that in front of the mirror is probably only right about here. And so it's probably a little difficult to tell if the image is actually in front of the mirror or on the mirror or behind the mirror. But this one, I think, does a much better job of showing you that it could be actually in front of the mirror. And this one here, I think, can do a good job of showing you that it can be upside down. And so, sure enough, you do see the image, and it's inverted. Okay? And that's where we're going to spend the time today, is looking at, okay, just like the flat mirror, where is the image? How big is the image? And so could you calculate in different scenarios? As I said, this mirror was kind of boring. We always had this relationship. What relationship do we have here? And so here is our image. Now let me throw a word in here. We're going to call this a real image. Some of you might recall that last time we called this the image, but we called it the virtual image. And the difference between those hopefully now becomes a little more clear. When we were talking about a real image, the light really did come from this point, didn't it? I mean, you could actually see where I have drawn the rays, and the rays actually converged there. Put another way, if instead of being an arrowhead, this was, say, a candle, and so light, a lot of light was coming from the flame, it would then be redirected right here. So if I put my finger right here, my finger would get a little warm, because the light is really there. If I put my finger here, does it get warm? No. And so the light is not really there. It has the appearance of coming from there. And so that's the difference between a virtual image and a real image. A real image, the light really was coming from that point. Now, maybe this makes sense for mirrors, because for mirrors then, if the light is appearing to come from inside of the mirror, then it must be virtual. Because can the light ever really be inside the mirror? No, the light hits the mirror surface and reflects off. The light never gets inside of the mirror. So we call this the virtual side of the mirror, the behind the mirror. That's always going to give you a virtual. If you ever get an image on this side of the mirror, it's got to be virtual. The light will only appear to be coming from there. The light would never really be on that side of the mirror. Fair enough? On the other hand, if the image is appearing to be in front of the mirror, which, as I said, is the less common scenario. But if it is being in front, as I think you could see with the ping pong ball here, then it's got to be real. Because the light would have to really have come together right here at this point and then spread out from that point. And so this is what we would call the real side of the mirror. So again, if we ever have an image formed in front of the mirror, it's got to be real. If we ever have an image formed behind the mirror, it's got to be virtual. And so those are going to be our two kinds of images. Behind the mirror, where the light appears to come from that point, or in front of the mirror, where the light was actually redirected from the mirror and then spreading out. Yeah.
When you have those light rays converging at the real image point.
Yeah, right. And then I don't mean to interrupt, and then don't forget, after they converge, they spread and they diverge from. So from this person's point of view, they are spreading out.
Okay, so does that mean that the image is bigger or that it's blurry, like from that person's point? Would you only see the real image right there at that point where they're converging, or do you see the image as you're backing up? Do you I guess I'm trying to be more clear about the rays as they're diverging, I guess.
Okay, let me get away from this picture for just a second, and let me look at that computer screen. Okay? When I look at this computer screen, the reason I see it, and the reason I say it's 3 meters away, is because the light is spreading out from that screen. Whether I stand here at 3 meters or I go back to 4 meters, the light is still spreading out. No matter where I stand, the light is still spreading out from that point. And so I can stand anywhere in this room and say that the light is coming from that point. Well, same thing here. The light is coming from this point. This person can stand anywhere they want. They will always see the light as diverging from this point. Did that help?
Yeah.
So it has nothing to do with where this person stands. It has everything to do with how the light was redirected from the mirror. And once it comes together here, that's where the image is, regardless of where this person stands. Okay. So that's what I want to do. I want to be able to calculate where is that image and how big is it. You can see in this drawing that it's upside down and smaller, but I bet I could get some numbers here after I go through some geometry.
Does every ray go through the focal point? It bounces off.
Well, not every ray. So, and I hesitate to make it too cluttered up there, but since you asked, well, I'll draw them and then erase them. But what about other rays? Just like Lester was saying, I only need to draw 2 to figure out where it's coming from, but everyone would do that. So, what would happen, and this is why I hesitate to draw multiple rays, because my drawings are not drawn well to scale. But let me give you another ray. What about the ray that went through the center? Shouldn't it hit the mirror and bounce straight back? Because the center is perpendicular to the mirror. And I wish my drawing was better. But that's a straight line. And unfortunately, I did not draw it well enough to scale to convince you that that third line would be coming from that point. Another ray would be the one that would hit right here. It would bounce off and go that way.
So that one doesn't actually go through the focal point at all.
Right. So not all the rays go through the focal point. In fact, only one does. Well, after, this is the only one that goes through the focal point after reflection. This is the only one that goes to the focal point before reflection. These other ones hit in all kinds.
So that's why it doesn't matter when you just told her where you stand because it's all.
Right. So no matter where this person stands, that's where the light appear comes from. It also is why I only need to think about 2 rays in order then to do my geometry to figure out where the image is. All of them will come from there. And maybe that's good for you to see, because not this week's lab, but next week's lab, you're asked to make some pretty hard drawings of the rays. And students usually struggle on it. It's a good struggle, because you'll learn a lot. It's, like forcing the baby chick to come out of the shell, and God, you just feel so bad for that little chick. You just want to break the shell open and help them out of that thing. They come out almost dead and exhausted. But we know from experience that if we help the chick come out, they die. And so I don't want you to die. So I'm not going to help you draw the rays. I'm going to let you struggle in the lab.
So the real image point that you have drawn up there, that moves around based on where the arrowhead is, right? The one on the left?
Ah, yes. And this is going to make it much more interesting than this one, because where the image is based on where the object is. How big the image is based upon where the object is. And in a much more interesting way than just always P equals Q. Yeah, and we can do a lot more with this type of mirror.
So if you were to move up above the image, could you see any reflection?
Oh, sure. Now, so this person essentially would really only see these 2 beams of light. And so this one that I've drawn is really just drawn for me to help me with my geometry. The truth is, this person is standing down here. They would never see this ray. Okay. And then likewise, I think what you were saying, if this person were to stand somewhere else, like up here, what that person would see is the light coming like this, which meant it basically came from here, hit the mirror in this little area, converged to that point, and spread out and went to their eyes. So the part of the mirror that becomes useful for that person is really right here. The part of the mirror that is useful for this person is really right there. But both of those people would still say the light is coming from this point. Just like in a flat mirror, that if somebody stands up here, they would be looking and using that part of the mirror, since the light would bounce off and go that way. And somebody down here would be using this part of the mirror as the light bounces off. But again, both people would say the image is right there.
Then is it safe to say that there's only one image per object?
Yes, it is very safe to say that. That's exactly what's going to happen. The image is formed by the rays being controlled by the mirror themselves, and the mirror only redirected the light back to a single point one time. And every observer is going to see the light coming from that point. There is not an image location based upon the observer's location. There is just an image location based on where the object is placed compared to the mirror. Yeah.
What do you call a mirror? What shape is the mirror where the real image is at the focal point?
The real image is at the focal point? Not sure I get. I mean, we can make it at the focal point with what we have right now. But I will hold off on that because that's the hardest to draw and the hardest to understand. But I'll do it in 5 minutes here. How's that? Okay. So now that I cluttered that picture up a bit, let me redraw it over here. Let's get into our first significant set of mathematics for the day, and let's actually then get an equation. An equation that says where is that image and what size is it. And so giving myself a little bit of room over here for just a second, you'll see why. I'm going to draw the focal point, the center of curvature, and my object. Again, let me emphasize, the object is further out than the radius at this calculation. That will soon change. But here is the ray that we drew first. It went parallel to the optical axis, bounced off the mirror, went through the focal point. The second one, we drew through the focal point and then made it go parallel, and that is where they meet. Actually, that's a much better drawing than the one I had before, because you can see the one through the center and the focal was almost a straight line.
Be straight, like the center, the real image, and the image.
Let's say that. What should be straight?
The points between the center, the real image, and the image. Should they form a straight line all the time?
Oh, here, here, here?
Yeah.
Yeah. They should always form a straight line, because a ray that left here and went through the center, when it hits the mirror, it's hitting the mirror perpendicular or incident angle of 0, and so it should go straight back, and so it's got to go through that point. Yeah. So they always should. All right, so this would be an upside down arrowhead. And so that's what we had about 5 minutes ago before we started talking about all these other arrays in here. But let's use some geometry, and I'll just make a couple of little triangles here. But just like we went through the geometry for a flat mirror, let's go through the geometry here. Let's put some symbols on here. The distance the object is from the mirror. What did we call it last time? What will we call it all the time? P. All right? How about the distance that the image is from the mirror? What shall we call that? Q. We did last time. We will continue that forever. What did we call the height of the object? H. What did we call the height of the image? H prime. So we will continue on each of those. Now, keeping that in mind and drawing what I'll call a set of green triangles, let me draw that green. And let's do some geometry with that. Since these are two lines that cross, these are vertical angles. And they're part of two right angles. So this green triangle on the right, I'll call it the smaller one, isn't it similar to that one? Because that angle is equal, which means those angles are equal. And so they are similar. Now, not congruent. I'm not saying congruent like last time. But I am saying they're similar. And they're definitely not congruent. They don't have the same length to them, the same size. But they do have the same angles. Yeah.
So for the curve mirrors, for the triangle that's up against the curve, we're always just going to approximate it, right?
Right. And remember, we made that same approximation to get the focal length. So I'm not changing anything, but it is an approximation. So is that exactly correct? No. Reasonably correct? Yes. And so we'll get some reasonably good numbers here. So as long as we're talking about small angles, less than 30 degrees, there is my set of triangles. What's nice about this, though, if this is the height of the image, I can translate that across, because you said it was parallel. That would be H prime for that triangle. So again, if I do a little geometry here, I can say H prime is to H. That side is to that side as this length. Well, that length would be designated as focal length is to, what's this length? Right, and so it's the whole object distance minus focal length, isn't it? So there's object length, P. There's focal length. You take the whole object length, subtract the focal length, and you're going to get that side of the triangle. So there is mathematically how those two are related. Let me do another set of triangles here. I'll do it in blue. Same argument that those two blue triangles are similar. No, not congruent, similar. Because they involve vertical angles here and they are part of a right angle. And again, not worrying too much about the curvature of the mirror, that's our small angle approximation. And again, noting across here that the height of this blue one would be h, I could again say h prime is to h. H prime is the side of that triangle is to that triangle as this distance. Okay, so what would this distance be? It's kind of fun. All right, so this would be image distance minus focal length, right? And then this length would be focal length. And here's what's nice about that statement. If I then do a little bit of mathematics here, these two have to be equal, right? F over P minus F is equal to Q minus F over F. And isn't that how P and Q would be related? So P and Q are related by F, right? We'll simplify the mathematics a little bit. If we cross multiply, we get F squared. If we cross multiply here, we got to do FOIL. So we have PQ there. We get minus PF there. We get minus QF there. And then we get plus F squared there. And so we've got our four terms from FOIL. F squared shows up on each side. That will go away. Let's take these two negatives and move them to the other side. And as long as I'm also moving them to the other side, why don't I also factor out an F? I'll pause there for a second because I think the next couple of steps aren't the normal steps you might have seen in an algebra problem. But isn't this saying P and Q are related? P and Q are related to F. Unfortunately, the way it's written now, they're kind of mixed together with the P's and the Q's. So it doesn't give me quite as much insight as I would like. So I'm going to do some more mathematics here to kind of separate the P's and the Q's and the F's. And fortunately, they can be. May not be quite so obvious till I take a couple of steps, but I'll write it as P over Q, and I'll put the P plus Q on the other side of the equation. Here's the part that I don't think you would have noticed without some kind of forethought here. What if I take the reciprocal of both sides? And the reason it does, the reason I'm going to do that is that puts the product on the bottom. Why? That's a common denominator, right? This is the same as 1 over P plus 1 over Q, right? If you were to add two fractions, first thing you do is get a common denominator by multiplying them. And then you would fix that by putting a P and a Q in the numerator. And so what we get is, I think, a simpler looking equation, albeit reciprocals, and so we have what we call a harmonic sum here, but the P and the Q are related to each other. It's why I left this edge of the board over here, because this formula, 1 over F equals 1 over P plus 1 over Q, is the mathematical connection between the object distance, the image distance, and the focal length. And although we've only derived it one time, before this chapter's over, we will derive that same equation 8 times. And so the neat thing to tell you now is this equation will work for all the cases of the mirror and all the cases of the lenses. Simply put, it's worth memorizing. That is the mathematical connection, as you will see, for everything in this chapter between the mirrors and the lenses we will be working with, even though it's the first time we've seen it. Yeah.
Can you explain again, sorry, the blue and green equations, A prime over H relationships?
Okay, the green one, I'm looking at 2 triangles. And so if this is one height of the triangle, H prime, and this is the height of the other, then similar triangles you can have a ratio. So the height of one is to the height of the other, as the length of one is to the length of the other. And then the same thing for the blue ones. And then of course a bunch of algebra. Right? And so again, let me emphasize it that this equation, commit to memory. I know it's the first time you've seen it, but we're going to see it again and again for the next hour and 15 minutes. We'll derive it as many times as we can. And it would be great if we could do all, well, either, depends how you count, 8 or 10 cases. But the real key is to tell you that is the key to figuring out the relationship between P and Q. Okay? And so that is our first step. Now, notice something here. Notice, by the way, that I have treated the P, the Q, and the F as positive numbers. Because right, when we do geometry, aren't we talking about the length of everything? So I have treated everything as positive numbers. That's fine. Until later on when I want to treat them as negative numbers. But I do want you to see that at this point, I've treated them as positive numbers. And this is my definition of positive numbers, right? My definition of positive numbers is the object in front of the mirror, the image in front of the mirror. Because you will soon see, what if the image is behind the mirror? There will be times where it will be useful to talk about negative values of Q. And negative values. In fact, why don't we do that right now? Why don't we ask this question? What would be the magnification of our image? How would we define the word magnification? We'll use the symbol capital M. But what are you really saying about magnification? Aren't you really saying how many times bigger or smaller is the image compared to the object? Aren't you really saying it is H prime compared to H? That's really the magnification. But let's do this, and it'll be very helpful. What if the object is upside down? What should we call the magnification? Negative. Oh, so here's going to be our first change in what we've seen up here. You see, I treated the P, the Q, the F, the H, and the H prime as all positive numbers. I'm going to change that a little bit here. Because let's use H as positive if it is pointing up. Which maybe I'll even say H prime also as positive if it is pointing up. But what if the object is pointing down? Well, to help me keep track of this, if it's pointing down, let's call that negative. And so if H prime is down, let's refer to that as a negative number. Okay, so what should I do to modify that? Would that change anything over here? Yeah, right. There is no H's in here, so that's not going to change anything. Fair enough? Now, it may change along in the derivation. You may come back over here and say, well, what you really meant then in this step, if you're going to let H prime be a negative number, then you really meant the magnitude of H prime there. Yeah, but they're still equal to each other. And so once I make this step, it doesn't matter, and therefore I get the same answer. So let me emphasize to you that this equation is then still valid when I let H be represented with a positive and a negative number. That doesn't change anything. However, it does become very helpful because if you see a magnification that is, say, -2, what would that tell you? Upside down and twice as large, right? What if I saw a magnification of +2? What would that tell me? It's right side up and twice as big. How about a -1/2? Half as big and upside down, which is kind of what this picture looks like here. If I was guessing just by looking at the picture, I would say this is a magnification of -1/2. Definitely negative because it's upside down, and definitely less than 1 because it is smaller. In fact, let's get a little equation here. Let's actually use then this definition for magnification and see if we can come up with an equation for the magnification of it. And so our definition, again, of magnification is how is the height of the image compared to the height of the object. Okay? Which kind of makes me want to use, say, this equation here, except the H over H prime, if you will, I guess would look like this if we did absolute values, wouldn't it? Because again, if we're letting it be upside down, then if we take the absolute value, we have to put a negative in front of it, right? And so that is F over P minus F, right? Oh, let me keep going. Remember this good equation over here? 1 over P plus 1 over Q equals 1 over F, the harmonic sum. Let me use that. Because if I rewrite this so that it looks like 1 over P over F minus 1, and I take 1 over F equals 1 over P plus 1 over Q, and there is my P and my F there. If I say multiply everything by P, I will get 1 plus a P over a Q is P over F. Let me use that back into this equation.
I'm sorry, did I miss something? You multiplied by a negative there, so...
Oh, shoot. No, you didn't miss anything. I got lazy. Right. Right. Yeah. And so so that should have a negative. Thank you. Which means it should be a negative there. Yeah. And then this magnification comes out to be -1 over, and then there's the P over F. So this is 1 plus P over Q minus 1. Well, the plus 1 and the minus 1 go away. And so all of this simplifies to a minus Q over P. And so let me put this over here on the board. That the magnification then is minus Q over P. Let me box both of these because box them again, box it again. Because you want to know the answer to all the homework problems in this chapter? Hey, you're looking at it. This two set of equations will explain all the mirrors. Now, we're going to have some rules to follow it, like when do we call H positive and when do we call H negative. But I think you got that rule. But that's just the beginning. But if you're willing to accept some of these rules that we are about to throw at you, then this set of equations will apply to every mirror and every lens throughout the chapter. That's kind of the neat thing about optics, is it's just one set of equation. It works for all the mirrors, it works for all the lenses, but there's some sign convention that we have to memorize. And that's why your author puts them in tables and just says what I'm going to say. Memorize the sign convention. If you don't get the sign convention right, then it won't work out right. But the sign convention is very useful. It tells you when things are upside down or right side up. It's going to tell you some other neat things too. And so the H and the H prime, whether it's positive or negative, I'm hoping that's the easy sign convention. When we start looking at positive and negative Q's and positive and negative P's and positive and negative F's, it's not so obvious, but the plus and minus for the H does make sense. It tells us whether it's right side up or upside down. Yeah.
For the original H, do we always, so it sounds like we're not always going to assume that it's just going to be positive, so that there will be problems where we're going to have an object that's upside down.
Right.
And we'll call that negative.
Right. Right. And so maybe I should show you what we've done so far. We've only done the simpler case of the advanced mirror. And so isn't that what you see? If you look at something far away, don't you see it upside down and smaller? I mean, if you look at yourself, I bet you will see it upside down and smaller. Fair enough? But let's keep going with this. What if it was a little closer in? I'm hoping you can see from this geometry then that as the position of this P changes, the magnification changes. Oh, but let's look closely at some of the math that what this has been saying to us. I'll kind of clear this off a little bit, but for the sake of discussion here, if I go to solve this equation for Q, and so my first step will say 1 over Q is equal to 1 over F minus 1 over P. If I take the reciprocal, that means I have 1 over F minus 1 over P inverted. Solving this in terms of a common denominator, I would get F and P here. I would get P minus P minus F there. Take the reciprocal. I would get an FP, and then this would be a P minus an F. Okay? Maybe it might be useful to take one more step here and write this as 1 over F times 1 over F, so that this is P, and then this becomes P over F minus 1. I don't know if that's better or not. Bummer. Yeah, maybe I should have left it in this form here. Maybe I'll go back a couple of steps. But here's what I guess what I want you to see here. If P is always greater than 2F. And so again, this is the case where I am looking at an object that is further out than the center of curvature. Okay, so if I'm further out than the center of curvature, then this number, which is 1 over F, minus 1 over 2F, or bigger. Okay? Actually, let's just say it's really big. Maybe I'll start there. If this is really big, can't we just kind of ignore that one? And then where is the image location? It is at F. And so something that is really far away, the image that is going to get formed is going to be at F. And hopefully that kind of makes sense, because when the object is really, really far away, the light comes in and gets converged to the focal point, or near the focal point. And then as the object gets closer and closer and closer, what's going to happen to the image? Right, and so as this gets smaller and smaller and smaller, we have 1 over the focal length minus a little bit, which means the reciprocal is getting a little bit bigger. And so the location is getting bigger and bigger and bigger and bigger. And so as the object gets closer in, the image gets further out. What eventually happens if the object gets all the way at the point of twice the focal length, at the center of curvature? 1 over F minus, maybe I'll do the math here, 1 over F minus 1 over 2F reciprocated. All right? That is, of course, 1 minus a half, so that is 1/2 of F reciprocated, which is 2F. Right? That is the radius. So where's the image now? At the radius of curvature. Simply put, what I'm trying to say is, in this first case, if the object is out here somewhere, the image is going to be formed between those two locations. And if we look at the magnification then, won't that always tell us that it is negative? And when P is very large, then the image is very small. As P gets smaller and smaller and smaller, as it gets closer and closer and closer, eventually when P is at the center of curvature, 2F, we just said the Q is what? 2F. And so what would the magnification be there? 1. -1, right? And I think that's what you saw in this hemisphere. I deliberately dropped the ping pong ball straight down from the hemisphere. This ping pong ball is at 1 radii away. So where's the image? Right on top of it, right? 1 radius away. And its magnification is -1. And so that's why we use the ping pong ball, because it should look about the same size. And when it's inverted, you can't tell when a ping pong ball is inverted. But when I hang half of a hemisphere, you will hopefully see it's the same size but inverted, right? Did you say yes? No? Oh, well, if I shake it, you will hopefully see how the magnification depends on its location. And at this point, I've only done the calculation for when the object is out in front of the center of curvature, which leads us into the next step. What if it is the other way around? What if we change this diagram? What if we take, and instead of having an object that is out past the center of curvature, here's the focal, here is twice the focal, there's the radius of curvature. Let me put my object right there. Here my object now is closer than the center of curvature. Will that change anything? Fortunately, not much, but it is a good next step. Let's draw the rays. All right? I'm going to draw a ray that hits the mirror. Bounces off, goes where? Through the focal point. Good. I'm going to draw a second ray. Which will it be? From the object through the focal, hit the mirror, bounce off and goes parallel. There will be my image. And good, you're noticing right away. What about this image? It's bigger. And interesting enough, the image is further out from the mirror than the object itself. And I think, without me getting into the math, you guys were already noticing that when I did this. Watch particularly when it swings in. What does the image look like when it swings in? Isn't it upside down and bigger? And isn't it looking closer to you than the object itself? And so the image does look closer to you. And hopefully our math will match here what we see. And so what kind of makes this interesting is not only do you get an image, but you get an image at times that are closer to you. I think that's always kind of the weird thing, that the image looks closer to you. But if you'll notice, the magnification of the image changed. When this is swinging in, the magnification, as we'll see, is greater than -1. And so this scenario is a lot like the scenario we just saw, except things are bigger and upside down instead of smaller and upside down. And so far we have seen things that are upside down and smaller first, and now we are seeing things that are upside down and bigger. Anybody want to guess the next two we're going to talk about? Right side up and smaller, and right side up and bigger, right? And then that will cover the whole scenarios that we have. So we'll have flat mirror, we'll have upside down and smaller, we'll have upside down and bigger, we will have right side up and smaller, and right side up and bigger. And those are our 5 scenarios. And fortunately, I'll keep saying it, those equations will work if we're willing to play along with some rules with our signs. Oh, a bunch of questions, yeah.
So for this one, the object is between the center and the focal point. So then does the real image end up being, does it have to be past the center?
Yeah. Okay. And we're going to say this is an image. We're going to say it's real, and I haven't done the math yet, but I think you are beginning to see from the geometry this is exactly the reverse, right? Where the object and image have reversed roles. The one outside is always bigger. The scenario I did before, it was the object on the outside which made an image on the inside. Now I've got the image on the inside, so I've got the object on the outside, image on the outside. So whatever's on the outside, whether it be the object or the image, is always bigger, and whatever's on the inside is always the smaller one. It's an easy way to remember it.
What happens when the viewer's closer to the mirror than the real image is? Like if I'm sitting...
Oh, okay, so I have been giving you the scenario as the observer is here. Yeah. The observer could be, say, here. And the light really hasn't come together to spread out.
Does that mean they don't see anything?
Yeah, it's a blurry mess. And in fact, this is probably the hardest one to show, but I'll try to show it. Here is the mirror. Actually, maybe I'll line it up here, because I know that this mirror has a radius of curvature of, well, it's an old mirror, so it is exact 1 yard. It's not quite a meter, but I'll call it a meter, but it's 1 yard. And so I'll turn the table kind of this way. But I have a meter stick here, which again is a little bit more than a yard, but I'll lay it out here. I will take then an object and I will hold it. This must be about the center, so that would be a hair in. And I don't know, can you guys see it that way? Does it look upside down and bigger? I bet if you look at it way out here, you would say it's upside down and smaller. But here, it would be hopefully upside down and bigger. How about you guys over here? Can you guys kind of see it then if I kind of move it this way? Yeah. And so it is upside down. And it is bigger. Okay? And so, again, we'll go, oh, shall we? Right here? Yeah. Okay, you can see it there? All right. But there, hopefully, is upside down and bigger. Over here, hopefully, is upside down and smaller. And so I can transition, which, again, is why I think this one is kind of neat to watch. Because if you look closely at that ping pong ball, you will see the image get bigger and smaller. And when does the image look bigger? Yeah, when that ping pong ball swings inward, huh? It looks bigger. And that's when the image appears to be closer than the object, too. Exactly. And so those are our two scenarios for today, what I'll call the two interesting ones we've done today, as opposed to the flat mirror. And so this is our third scenario. But let's go through some numbers. And let's go kind of quickly here, because fortunately for us, there's really not any new mathematics compared to what we did last time. This is just the image and the object reversing positions, so the equations we get are the same. And so not a surprise we end up with the same equations. It's probably worth repeating. Let's draw a set of green ones again. Here would be a set of green triangles where, again, they're right triangles. These angles are equal. If we call this then the height of the object and P the object distance, then this distance here is Q, and this, the height of the image, H prime, is the same as that one. So if I go, the magnitude of H prime is to H. Okay, so notice now I'm just going to do my geometry based on absolute values. What is the height of it? Because H prime really should be labeled as a negative number here. So H prime is to H as focal length. Oh, and I should have done this in green. Keep it coordinated there. As focal length is to P minus F. And isn't that the equation we had before? I've erased it on the board, but you guys have it there in your notes. Isn't that the same one we got before? And then let's do the blue triangle. The set of blue triangles would fit right here. And again, I can say H prime magnitude is to H. And so H prime is to H as this distance. Well, that would be Q minus F is to F. And if we set them equal, we have F over P minus F is equal to Q minus F over F. And since that's the same equation we had last time, isn't that just going to get me 1 over F is equal to 1 over P plus 1 over Q? And so without me doing all the math again, can I just point to that and say, look, that's going to be the relationship between the P and the Q and the F. And then we can go ahead and we can derive the magnification, and we're going to end up with that same number here. And so there's nothing too much more to add to this one other than to point out this is the scenario where you will get a magnification greater than 1. You could even see that if we run through the math. Maybe it's worth kind of doing a couple of steps here in the mathematics in terms of the magnification, watch this. If I have m for magnification, which is a minus q over a p, and I also keep in mind that 1 over f is equal to 1 over p plus 1 over q. Then if I try to solve this for, say, a q over a p, I can say q over f. Actually, let's not. Let's do it in terms of q. I'm going to write this as a negative 1 over p. And in place of q, let me write 1 over f minus 1 over p, and then take the reciprocal of that. Okay, because 1 over f minus 1 over p is 1 over q, and then I can take the reciprocal. So this is, again, a negative 1 over p. This would be a common denominator of fp. This would then be a p minus an f. Take the reciprocal. So negative 1 over p. This is f over p. P minus f goes there. The p would cancel off, and I got minus f there. And the top, I get a p minus an f there. And so this would be the magnification. And now maybe you can see it better. I probably should have done it this way the last time. Is what if p is greater than f but less than 2f? Right? And so it's in between. So the object is greater than f but less than 2f.
You'll get a negative magnification.
Right. This number here would be like, say, 1.5f. You subtract an f, and you are at a fraction of f. The f's cancel off, but then you have 1 over a fraction. That's a number greater than 1 with a negative in front. So this will give us a magnification that in terms of magnitude is greater than 1, and in terms of sign is less than 0. And so that's what we had said earlier. What would happen is if the object was between the focal length and twice the focal length. This is the one that gives you upside down and bigger. By the way, the same mathematics could be applied to the first scenario I did, where the object is greater than. And so if p is greater than 2f, what do you notice there? Yeah, if that number is greater than 2f, then when you subtract an f from it, you get something greater than 1f. The f's cancel, but you have something greater than 1 in the denominator. So in terms of magnitude, it is less than 1. It is upside down, so the magnification is obviously less than 1. So both these scenarios make it upside down, but this scenario makes it upside down and bigger. This scenario makes it upside down and smaller. And again, I'll come back to this one, but I think you can see the transition really well when you take this hemisphere straight down, because this hemisphere straight down is at the radius of curvature. And so when it swings in, we are at a position that is less than 2f. And when it swings out, we are at a position greater than 2f. And so you will see that the magnification goes negative always, but when it swings in, it's greater than 1, and when it swings out, it is less than 1. And so you could actually see the image change its size a little bit as it swings around there. And as the object swings in, the image comes out and looks bigger. Now let's change it up a little bit. Let's go ahead, and maybe I could leave this one on the board. It would be nice to compare it to where it gets a little more complicated. What if we are inside the focal length? What happens then? Are you bored? Yes and no. It'll be a lot shorter for the convex mirrors. Yeah. So, but let's look at this next scenario where we take a mirror and we put the object, as you guys are asking the next natural question. That's good. All right. What if we get even closer? What are we going to see? Well, this one gets a little bit harder, but can still be done. Help me with the first ray. What would happen to the ray when I draw it straight and hits the mirror?
Comes down but doesn't cross
No, yeah, that one's going to go through the focal point.
almost the angle.
But remember, I'm drawing a normal to there. So the angle of incidence looks somewhat like the angle of reflection between my imperfection drawing. I think it's close enough. If my partner could just draw better, they would look better. But my partner keeps making mistakes, just like inlet.
Artistic ability.
What?
You were left-handed, right? So you're a right-brain person.
Well, I am clearly evident that that theory does not hold. I don't know with that right-handed thing, but I am left-handed. I may be controlled by my right brain, but I have no artistic ability and very little artistic interest. So that's right. Yeah. Anyways, there is the first ray. The second ray is much harder. Oh, good. Good. See, we've been drawing the one that goes through the focal point and bouncing off. But if you look closely at this one, we don't want to draw the one that goes through the focal point, because if you draw the one that goes through the focal point, it never hits the mirror. However, right, you could draw a ray that does hit the mirror coming at the same angle as if it went through the focal point, right? I mean, it doesn't have to actually go through the focal point. There's nothing magical about the focal point itself. We were just drawing it through the focal point so it would hit the mirror, and it would hit the mirror at an angle we knew how to draw. And so I'm going to do the same thing. It doesn't really have to go through the focal point, but what it does do is if it is coming up at an angle as if it came from that focal point. The key part is that it hits the mirror. And that it hits the mirror at the appropriate angle. The appropriate angle being as coming from the focal point. All right? Because what would happen to that ray? Right, and that one would bounce off and go parallel. And so what would somebody standing over here see? Yeah, left eye, right eye, trace them back. Where do they come from? Behind the mirror. And right side up. And bigger. And so we are got the next piece of our puzzle. We have right side up and bigger. We still need right side up and smaller, but we've got upside down smaller first. Then we got upside down bigger. Now we've got right side up bigger, and soon we will have right side up smaller. But this would make it right side up and bigger. And as you guys pointed out, what kind of image is this? Yeah, this would fit the word virtual. This is a virtual image. The light never really came from behind the mirror. It has the appearance of coming from behind the mirror. And so anything that gets closer than the focal length begins to do that. So again, turning to our big mirror here, moving the flashlight, maybe, well, you guys tell me, is that close enough? Let's see. So about 1 yard. That would be about half. So this would probably be a good spot here. Can you see it? And is it right side up? Is it bigger? Yeah. And so I should get right side up and bigger. And so again, the optical engineers have some decisions to make. What do you want to do? What do you want to get accomplished? Do you want to make it look bigger? Do you want to make it look smaller? I think you might be a little more familiar with this type of scenario. This, where would you see? I know where you're going, but no. Wrong mirror. Hold on with that. Right answer, wrong question. Yeah, makeup mirrors come to my mind here for you ladies, or you gentlemen if you have makeup mirrors. But if you have a curved mirror and you get real close to it, ooh, that's scary because it will make things bigger. And you can see the pores and all the other wrinkles and all the other things that, well, you guys are too young to have wrinkles, but for somebody, so you get real close to there, you can see that magnification. And so that is one clearly a good place for it. Another good place of the magnification, not so much noticed because it's not so much as optics as it is radio, but what about these satellite dishes? Right? You try to then control the light coming in into the focal points. And so you put that little receiver here on your satellite dish at half the radius of curvature. So the radio waves that are coming in from the satellite come in and get focused and concentrated to a point right here, and that's where you put the little detector. And so that little detector should look like this little light source we had earlier where the light comes together. And that's a little bit different because we're not trying to form an image, we're just trying to concentrate the light. Your headlights on your car, kind of the reverse also, not really trying to magnify them, but if you put the bulb right at the focal point, what will happen when it hits the reflector? Come out and be parallel like this, right? They'll actually have a different curvature in this dimension than this dimension. So when you put the bulb here, the light comes out pretty parallel up and down, but still spread out left or right. So the headlights in your car are spread out. You can even see the cone reflector in the flashlight. It's trying to get the beam to be relatively straight, relatively parallel by putting it right in there. The dentist chair is another good example. They often have a little mirror. It's kind of rounded on the end of the handle, kind of hooked a little bit. But if you're between, whatever the dentist does, they come in, they do their thing, and then they got to let the filling set or whatever, and then they move on. Pick it up. Don't tell them. But look closely at it, and you'll see that little mirror is indented just slightly. It is a concave mirror. And so when the dentist puts it in your mouth, it'll magnify the teeth in there by a small factor. I think it's about a factor of 2. And so as he's checking it out, he can use the mirror to see around back, but it can also magnify it too. And so it's got a magnifying effect to it. And so that's what you're seeing here. And as I claimed, we can still use this set of equations here. If. Well, let's run through the math here. Let's use the same kind of symbolism. Let's call this distance still P. Let's call this distance still Q. Let's call the height of the image still H prime. Let's call the height of the object still H. Let's draw some triangles. I'll start with a green set. And I'll see if I can match it to this green set here. But I will draw this triangle and this triangle. So we have a small green triangle superimposed inside a bigger green triangle. And that goes straight down. The mirror is barely curved. So there's our approximation. Okay? But you will notice that this height here is the height of the image. So if I say height of the image is to the height of the object, and let me pause right there. They're both positive numbers, aren't they? So I'm not going to worry about absolute values for this little scenario. This one is not inverted. So height of the image is to the height of the object. So this is to this as what? Yeah, this distance, which is the focal length, is to this distance. Well, what's this distance? Yeah, that could be written as f minus p. Does that look like this equation? Remember the absolute value. It is the same equation, isn't it? That would be the advantage. If I write this over here as a negative h prime over h is equal to f over p minus f, taking that negative and putting it into here, I would have h prime over h, f, and an f minus a p. And so it really is the same equation. And so using h as a positive and negative number has a nice advantage in that sense. Not just in a sense that it tells me if the thing is upside down or right side up. It has a nice advantage that this scenario is starting to look a lot like this scenario, which hopefully will give me the same equation. Because it would be great just to have one equation and not have to worry about whether the object is in front of the focal length, behind the focal length. I can figure it all out based on the same equation. And that is what's going to happen. That set of equations will still work. Let's do the blue triangles. The blue triangles would be a triangle that would include the height of the image, and the height of the object would be buried in the height of the mirror right here, and so that is h. So again, using my blue pen to calculate that, again I have a set of similar triangles. I have height, oops, sorry, I'll start over here. Height of the image is to the height of the object. As what? As this plus that, right? Now, let's be careful here. If you say plus, don't you really mean absolute value? You mean the absolute value of p plus the absolute value of q, right? You mean the total distance of them. Okay, more on that in just a second, but there would be the two added together. Huh? Oh, thank you, thank you. F. Yes, F. My bad there. Oh yeah. So F plus Q. And then over, no, so which one did I do? Oh, so I just did this one. Over the F. Now, the F with the absolute value signs is not really needed. Because didn't we say F was already positive way back? We go, okay, F, okay. But here's my question for you. Does this blue equation look like this blue equation? Almost. I mean, first of all, let's come back up here and do the same thing with the absolute value that we did with the green one. Doesn't this really mean negative of h prime over h is equal to q minus f over f? And if I put that negative into here, doesn't that really mean h prime over h is equal to f minus q over f? Okay, so using the negative sign with the h, I have an equation that almost looks like this one. Well, what's just shy? So what if we call q negative on that side of the mirror? Because if we do call Q less than 0, then we can write this as F minus Q, right? And then doesn't this equation then look like this equation? Which, without doing the math, wouldn't that give me those relationships? So wouldn't that still work? But what do I need to remember then? Q is negative when the image is virtual. And if you're willing to accept that, then you get the advantage of that equation applying to all three scenarios. And you don't have to keep track of what scenario. You can just plug and chug into the math. But you do need to remember that H can be negative and Q can be negative. Like I said, the first one is probably the H is the easiest one. When is H negative? Upside down. When is Q negative? Yeah, when it's on the virtual side. But even though it may be a little hard to remember pluses and minuses, keep in mind, this is a great advantage. What if you went through a bunch of calculations and you finished and you found Q was a negative number? What would that tell you? It's virtual. So treating Q as a negative number may be a little bit hard to memorize at first, but it has some huge advantages. And those two are the big advantages. Number one, it's going to give you the same set of equations for this scenario as every scenario, and you don't have to look at and try to remember, oh, is this a special case? Is this a special case? That set of equations will work no matter where the object is. And the other neat thing about it is you could just go ahead and solve it, and if you come up with a negative Q, that tells you great information. What does it tell you? It's virtual. And look what happens over here with the magnification. What if Q is a negative number? What does that tell you here? The magnification is positive, and that's what we have here. And so things that are upright must have virtual images. They must have Q's that are negative. And so the sign becomes a really powerful tool, both in the H and the Q. And we haven't got there yet, but yes, there's going to be a negative F. And the hardest one, yes, there's going to be a negative P.
What?
Let's hold off on that one. But all of these can be positive and negative. So again, a negative H I don't think throws anybody for a loop. Even the negative Q is not too bad. People go, okay, well that's just plus and side of the equation and minus side of the equation. But the negative F, and particularly the negative P, can throw people for a little bit of a loop here. So, more on that in just a second, huh? No. We'll see that scenario here in just a second here. But, better keep going here. Maybe we'll have to go a little faster with the lenses when we get to lenses next time, but the idea, though, hopefully is going to be the same thing continued on here. So that is the, I guess, the end of what we can do with our concave mirrors. Pull this back a little bit more. But we're still missing, yeah, and we're not going to get it with this guy. Because we've just studied every case in terms of the concave mirror. And so let's go to this mirror. No, not that one yet. But let's look at this one. In fact, I'll just take this hemisphere and turn it around. What do you notice?
These guys are closer than those.
Oh, and actually, did I do a right side up bigger? With this one? I did, didn't I, or no? Yeah. Oh, who's closer? Oh, the flashlight, we got it real close. Okay. And so you'll see it right side up and bigger. But let's look now at this one. And this is, as you said, our final scenario. What do you notice? It's right side up and smaller. But to see this one in action, it's probably worth starting back at the very beginning, where instead of having a curvature that is curved in, which we call concave. Let's have a curvature that is out, which we'll call convex. And so let's come back to our little laser beams here. Let's turn off the house lights here. Let's put, and erase that focal point. And of course, we have a spreading out. Sometimes that's why we call this the divergent mirror and the other one the convergent mirror. Your author uses the shape of the geometry, so I'll try to stick to that. But this would be the convex mirror. And so as it spreads out, notice we don't have a place where all the light comes into focus. However, we do have something equivalent. What do you notice about these rays? This ray right here looks like it's coming from back here. This ray looks like it's coming from back here. This ray from back here, this ray from back here, and that ray from back there. And so this is my mirror. I do not have what we would call a real focal point, but I have a virtual focal point. It is as if the light is coming from that point. The light never really does come from that point, but it is as if it is coming from that point. Keeping that in mind, then, let's draw some rays. Are you looking for your test? Yeah, over there. All right, so let's go ahead and draw this scenario. Actually, I'll do with the black one here. And so I can save my green and blue one for what we've been doing with the triangles. Let me go black here and do this. And so I am going to do the same type of notation that we did for the concave with the convex. I'm going to put an F there for the focal point. It's really more of a virtual focal point. Sometimes people will put a VF instead of just an F, but I'm just going to do an F there. That's what your author does. I'll also put right here a C for the center of curvature. And let's put the object out here. I'll start with pointing out that this object can be anywhere out here, but it can't be past the focal point, right? It can't be on this side of the mirror. So that's why this mirror can only do one thing. And so the last mirror, we did three things, right? The last mirror made things upside down and smaller. Then it made them upside down and bigger. Then it made it right side up and bigger, depending on the location and where it was positioned compared to the focal point and the radius of curvature. We had three little sections. This only has one section, and that's why I can only do the very last thing, and that can make it right side up and smaller. That's all it can do. So this one's kind of boring too. Not quite as boring as the flat mirror, but only does one thing. Don't get me wrong, it has its advantages, but it only does one thing. And so let's draw some rays. I think this one is the hardest one to draw. That's why I saved it for last. But here's the ray that goes parallel. What would happen when it hits the mirror? Does it bounce off and go through the focal point? Right. It doesn't go ever into the mirror. It bounces off the mirror. And it bounces off in such a direction as if it was coming from this virtual focal point. That's why we did this little picture right there. So we could say that's where it appears to be coming from. And now maybe the hardest ray of all. What about the second one? Actually, I could do the center one. I've been avoiding the center one. But if you choose, remember we only have to do two. But if you want to do the center one, you can. But I'm going to avoid that one. That's not the one I'm going to draw. Because I think it's easier. Especially since I want to see how it matches this one. Right. The one that is headed towards the focal point. What's it going to do when it hits the mirror? Yeah, it will bounce and go parallel. So hopefully you will see it's kind of like this scenario, but it doesn't actually go through the focal point. It can't. The focal point is a virtual focal point. But what would somebody over here see? Right, they would trace this ray back and this, I'll start with this one. If you trace that ray back, it's somewhere over here. If you trace this ray back, it's this. So what you get is right there. And so you get a virtual image. You get an image that is inside the mirror. But the neat thing about virtual, what did we say earlier? If Q was negative inside, the magnification is positive, and this will be upright. But in this case, it'll be upright and less than 1. And so if we go back to our geometry again and create a set of triangles, I'll start with green here, and say, let's go ahead and look at, so I can maybe color code them correctly. Why don't I go ahead and do green triangle into here. This ray that was coming down would have gone through to the focal point. That was the intent of that drawing. And so I will make a small green triangle inside of a big green triangle. Let me put some notation on the board. Again, just like before, let's call this P. This is the distance the object is from the mirror. This is the Q, the distance the image is from the mirror. This is the focal length, virtual focal length, if you will. This is the height of the object. This is the height of the image, which is the same as that little section. And so if I apply my geometry to this triangle here, I can say height of the image is to the object. So that's this little triangle. Height of the image is to the height of the object as this distance, well, that's focal length, is to what? This distance. P plus F. Now, does this equation look like this equation? Almost, right? Is there anything I could do to maybe make it look like that so that it will look like that? Yeah, what if we call f a negative number here? You see, I just did this geometry and I actually treated everything as positive. Now, the h's are already positive. We talked about that. So there's no point in putting absolute value signs there. But if I let a mirror that is convex be mathematically represented with a negative number in this equation, that means this can be written as negative the focal, P minus negative the focal. Move the negative over to here, and negative H prime is to H as F over P minus F. Isn't that what I have over here? And so here's the lesson, and here's the point, that we can continue to use this equation, which is eventually going to lead to this equation, if we're willing to do what? Can F positives and negatives. And so F is negative when we have a virtual focal length, when we have a convex mirror. Now again, the disadvantage is we need to remember that, but the advantage is not only can we use that set of equations, but what if we're solving a problem and the problem is, well, what kind of mirror do you need? And you go through the math and you finish up and you get F equals a negative something. Tells you need a convex mirror, exactly. And so the information that is in the positives and negatives can be very useful. And so like I said, at first it looks like this is a hassle to remember whether it's positive or a negative. But if you remember positives and negatives, it becomes a really strong advantage. Like I said, it allows you to use the same equation again and again and again. And the negative sign has information in it. It tells you if you're solving for whether this is a concave or a convex mirror. Yeah.
Does this mean Q has to be negative also? F is negative?
Oh, now we've already said Q on this side would be defined as a negative. So we need to stick to that definition.
So it has to be.
So it has to be negative. And so my next triangle, blue, is going to have a Q's in it, and I got to remember that I'm already treating Q as a negative number. But that's going to be good, because if I do continue to treat Q as a negative number with F as a negative number, you will see that I will get this equation, which means when I put the green and the blue together, I would have that, which means this equation will still be valid for the convex mirror, and we will only have one set of equations. Many of you might remember from Physics 102, I think that was the challenge in Physics 102, was keeping in mind what set of triangles should I use when I have concave versus convex. The neat thing here, that will go away, right? We know this, that set of equations will work whether I have concave, convex, whether I'm closer than the focal length or further out than the focal length. Same set of equations. The only thing I got to remember now is when is H positive and negative? When is Q positive and negative? When is now F positive and negative? And we haven't got to when is P negative, but that's next. All right. So let's do the blue triangle here. The blue triangles would look something like this. I would have a small inner blue triangle and a bigger blue triangle. And if I write that out, I can do something like this. The height of the, I'll do the small one first so it looks the same. The height of the image is to the object. So height of the image is to the object as this distance. Well, I'll write it first as F minus Q. But when it comes to geometry, what I really mean is the absolute values of F minus the absolute values of Q's. And that would be this, and then over this distance, which would be F, which I will write as absolute value. And you can kind of see over here that that blue one is beginning to look a lot like that one. In fact, it's almost identical, except it doesn't have the absolute value signs. So let's use our notation here and call this a negative F, because again, we're going to treat this as a negative focal length. And so this becomes a negative of a negative Q, and this becomes a negative F. Which, again, if you take that negative and put it up here, that becomes a plus F minus Q over F. And isn't that the same thing as I've gotten over here? And so, again, if we're willing to accept F as being a negative number in this case, we can get the same set of equations. And that will be the real advantage here. And if we think about the magnification again, the magnification, which is minus a Q over a P, which, I should have never erased the magnification. Let me do it again. Negative 1 over P. Q would be 1 over F minus 1 over P reciprocated. Negative 1 over P, common denominator is F and P. This is P minus F. Take the reciprocal. Minus 1 over P. This is F. This is P. This is P minus F. P's cancel off, and you get minus F over P minus F. If you look at this equation and the magnification and you apply it to this convex mirror, you will see that, what do we say about F for the convex mirror? It's negative. So a negative and a negative, that one's going to be positive, right? And treating P as only a positive number, because that's all we've done so far, then I will get a negative and a negative here, so that will make positive. So I got a positive on top and I got a positive on the bottom. I can only get positives. And so this mirror only makes things right side up. Nothing else. And, right, this number is always going to be bigger than that number. So it's always going to be smaller. And so the math does match what we were saying earlier. In fact, as we finish this mirror, maybe I should ask, where do you see mirrors like this? Okay. The one advantage I hear from a lot of you is the wide angle. And so you see it in, I heard somebody say, blind spots in supermarket stores, so you can kind of get a wide angle view of what's going on. Fair enough. Of course, the disadvantage is everything looks small in there. I always wonder in convenience stores if it really helps. I mean, it's way back in the corner and it, you know, got this curve to it. So, yeah, you can see down every aisle, but it's really kind of small. So can you really see if anybody's shoplifting or not? I haven't been curious enough to try the shoplifting yet, but kind of curious if there's anything in there. But yes, that's the nice thing about these mirrors. They are wide angle. And maybe an advantage or disadvantage is they make things smaller. So you see these probably more common. I heard somebody say your passenger outside mirror there. That side mirror on the passenger side. If you ever look real closely on the writing, what does it say on the mirror? Objects are closer than they appear. Because that mirror does have a little curve to it. Some are curved enough that you can clearly see that it's curved. Some are just slightly curved that it's sometimes hard to notice. But it is curved enough that when you look in that mirror and you see a reflection of a car in the lane next to you, it will look small. And if you're not careful, you might think, hey, it's small, so it's way back there. And so I'll just come on over, and it may not be way back there. It may just be small because the mirror is curved. And so that's why the little description there is, hey, you know, they may be closer than they appear to be. And of course, you said the other one, where's a big place you see, or maybe you don't see them, ladies see them. Where do you see these mirrors? Dressing rooms, right? You can imagine this mirror being, instead of a sphere, but a cylinder. So it's curved this way, but not curved this way. So if I were to stand in front of a mirror like that, it would give me the same vertical height, but smaller in width, exactly. And so my width would be reduced, but my height remains the same. And so you're definitely going to buy that outfit. Boy, look at that outfit. Look 5 pounds lighter in that one. And so just enough curvature to make you buy it without noticing that it's curved and that you're in a big hall of mirrors, and it's nice market ploy to get money from you. Well, bummer. I did not in any way get to the lenses, but I did, I guess we'll have to wait till next time, want to pass this one around because we haven't mentioned, what about P? Can P be negative? And I keep saying yes, but I guess I haven't shown you, and I guess I will show you Thursday. So that'll be your cliffhanger. I know you won't be able to sleep for 2 days, but come back and you'll figure it out.